So I'm back with another one of the concept bite videos, this time on Excimers and Exciplexes. This is just an example of an emission spectrum. Just a regular emission spectrum from any particular molecule that we might see. But a feature of Excimers is that as I increase the concentration, I start to see a broad Gaussian band growing in at low energy. So I go from this band with fine structure, which I'm trying to approximate here, the emission spectra of pyrene. And I can see that the intensity of that drops, and I see this formation of this band. Now you'll notice my y-axis here is called normalized intensity. That's just how much emission I see divided by how much absorption I have at that excitation wavelength, which should accommodate for concentration effects. It should always be the same if we think back to the Kasha-Vavilov rule. But if I increase the concentration of something, sometimes I see this high intensity, broad, featureless, Gaussian peak grow in at a lower energy. And this is characteristic, if I've only got one thing in solution, of Excimer formation. So my next slide, I've got that same kind of figure, but I've tipped it onto one side because now I'm comparing it to actually what's going on in terms of the energy levels of my molecules. This set of kind of fine structured peaks that I see at high energy is my monomer emission, and that is just my emission from this flat part of this green line down to the pink potential well. It's just my regular fluorescence or phosphorescence that I see from a molecule. But the thing about an excimer is that my excited state can have a lower energy if shared across two molecules. If it has a lower energy, I start to get into this region of a potential well. And then I start to see emission, not from my excited state to my ground state. I start to see my emission, which is basically moving from this excimer kind of dimer of two molecules brought together with a lower energy to the ground state of that, which is just these two molecules diffusing away from each other. And as I look at moving across these different energies, this is the origin of this broad Gaussian peak. It's because it's coming from this very symmetric potential well. I see excimers in the emission spectra of things, but I never see them in the absorption, because absorption always happens from the monomer. The molecules are not stable as a dimer in the ground state. So the absorption spectra is unchanged. So here I just have an example of what an excimer, can look like. This is a pyrene excimer, the thing that I've been approximating the emission spectra of before. And my two planar conjugated systems just stack one on top of each other. They have a well-characterized separation, about 3.5 angstroms, which is the van der Waals distance. So as close as we can get their electron clouds before we form a more formalized bond. And in this excited state, they're relatively stable. They're stable for nanoseconds, which is quite a long time in terms of photophysics. We can get excimer formation from both singlet and triplet states, and they have to be in solution, or they have to be able to kind of diffuse and meet. I can't get them forming in the solid state because I can't get these two monomers moving around and forming a dimer complex. So if I freeze something, the emission I see is never going to be excimer emission. They form at high concentrations because of that limit of needing to diffuse within the lifetime of the excited state. So the higher the concentration, the higher the probability of being able to form that excimer dimer. Exciplexes are incredibly similar, but unlike Excimers, where I have two identical molecules, an Exciplex is essentially formed of two dissimilar molecules. And because those molecules are dissimilar, they have a different tendency to want to attract an electron. And so we end up with a slight charge separation. Now, this can go on further, and I can actually end up with dissociation or electron transfer happening within my molecule. But the Exciplex, the bit I'm interested in here, is this charge-separated donor-acceptor complex. From this charge-separated donor-acceptor complex, I can have emission just the same as before. This complex is stable upon absorption of a photon. So my donor absorbs a photon, it will then form a complex with the acceptor, and there will be a slight redistribution of electronic density between the two molecules. I can see emission from that as it emisses from this Exciplex state. My donor and acceptor will diffuse away. So it has a lot of the same properties as an Excimer, except now I have two different molecules. In terms of wanting to be able to form this Exciplex, wanting to be able to form this slightly charge separated state, polar solvents are what I need to do it. Non-polar solvents are what I need to do it, because polar solvents tend to want to have that ionization going to completion rather than supporting the slight charge redistribution. Again, just like with Excimers, I don't see any difference in the absorption spectra because I'm absorbing, the donor is absorbing the light in this case to form an excited state donor. There is no kind of formal bonding between donor and acceptor in the ground state. It's only in that Exciplex state. I hope this has been helpful. I'll be back with more.